Hello everyone. Today's class we will discuss a few topics. Okay? First topic is the unit of rate constant or unit of rate of reaction. Now what is the unit of reaction? As we know, the rate, that means R, equal to change in concentrations of reactant divided by the change in time. Since it is change in concentrations, no, concentration is mole per liter and change in time is nothing but the time, that's why second. That's why the unit becomes mole per liter per second. Now in gaseous states, the rate of a reactions can be expressed in terms of partial pressure, which is atmosphere per second. Atmosphere means the unit of pressure, atmospheric pressure. Okay. Now how can you calculate this one? Atmosphere ATM, not atmosphere, ATM per second. Since we know for gaseous state PV equal to nRT, okay, ideal gas equation PV equal to nRT. If we say PV equal to nRT, then P equal to NV by RT. Okay. Now NV is the concentrations of a particular gas. Therefore P becomes CRT. C is the concentration, R is the gas constant, T the temperature, and P is the here partial pressure. Then C becomes P by RT. Since RT is constant, that's why you can say C is proportional to P. P is the partial pressure, and from that partial pressure we just use the unit of partial pressure is the ATM, atmospheric pressure. And second inverse, since no dx by dt, here C means in terms of partial pressure it is ATM divided by S, that means second, ATM per second. Okay. Next is the what are the factors affecting the rate of a reactions? That means on which factors the rate of reactions depends. First factor is the concentration of the reactant. If the concentration of reaction is high, then the rate of the reaction will be high. That means if the concentration of the reactant is increasing, then obviously rate is increasing. That's why concentration of reactant is proportional to the rate of the reaction. Remember, rate of the reaction is denoted as small r. Now surface area is also proportional to r. Presence of light is also proportional to r. Now second one is the surface area. Now see, surface area means suppose let us take an example, a molecule. Okay, let us take an example. Suppose this is any atom. Okay, this is the surface area of the atom, which is spherical in size. Suppose here is another atom which is smaller size. Now according to your level, that means according to your level, just know that when the size of a particle decreases, that means size of the particle decreases, surface area increases. Okay, when the particle size decreases, surface area increases. Okay, now if the surface area increases, that means the reaction now can have more space to react. इसका मीनिंग क्या है? अगर सरफेस एरिया डिक्रीज हो रहा है या फिर इस सरफेस एरिया अगर इंक्रीज हो रहा है तो इस तो रिएक्शन होने के लिए ज़्यादा स्पेस है. अगर ज़्यादा स्पेस है तो मॉलिक्यूल रैंडमली मूव कर सकता है. अगर मॉलिक्यूल रैंडमली मूव करेगा तो रिएक्शन इजी से होगा और रिएक्शन का रेट प्रोपोर्शनल होगा. दैट मीन्स डायरेक्टली प्रोपोर्शनल. इफ सरफेस एरिया इंक्रीजेस, रेट ऑल्सो इंक्रीजेस. नेक्स्ट, presence of light increases the rate. Presence of light increases the light, because light also has an energy which is what? Solar energy. Okay. Second thing, nature of the reactions. For example, ionic reactions are very fast because they are already present in the form of ions in the aqueous solutions. Since the ionic solution or ionic reactants contains the ions, that's why the reaction will be faster in the ionic condition. Okay, see the next is the temperature. Temperature is also directly proportional to rate of the reaction. That means temperature increases. When temperature increases, the rate of the reaction also increases. Second thing, last thing is the presence of catalyst. Remember, catalyst is a substance which does not takes part in the reaction, but it enhances the speed of the reaction. Okay. Catalyst generally increase the rate of the reactions, chemical reaction. In case of reversible reaction, it does not alter the positive position of the equilibrium, but helps achieving the equilibrium quickly. What it means, in case of reversible reactions, the catalyst does not alter the position of equilibrium, okay, but it helps to achieving the equilibrium quickly. Next thing is the rate of a reaction in terms of stoichiometric coefficient. Rate of a reaction in stoichiometric coefficients. First, let us take an example here. A is the coefficient of this one, A reactant, capital A. Small b and capital B. Small b is the coefficient of capital B, and reversible reaction goes to C plus DD. Okay, C and D are the coefficient of C, capital C and capital D respectively. Now, what is the rate? Rate equal to minus signs means it is in reactants. Since reactant is decreasing concentrations, okay, since the concentration of the reactant is decreasing and the concentration of the product is increasing, that's why it is minus 1 by A D concentration of A by dt equal to minus 1 by B. This one is the reactant for A, this one reactant for B, this one product for C, this one product for D. Since these are in reactant, that's why here is minus, these are in product, that's why here is positive. Now, where A, B, C, D are the stoichiometric coefficients. It is in stoichiometric definitions, but actually rate is defined as rate is proportional to the concentration of the reactants. Suppose in these reactions A and B react to produce C and D. Here the concentration of C to the power X, concentration of B to the power Y, where X and Y may or may not be equal to the stoichiometric coefficient of small a and small b of the reaction. Okay. Now rate is what? Rate is the D concentration of R, that means change in concentration of reactant divided by change in time. Since it is reactant, that's why here is minus, and if we withdraw this proportional that, we have to apply a constant K. K is known as the what? Proportionality constant, called rate constant. Called rate constant. Now, rate law is the expression. What is the rate law? Rate law is the expression in which reaction rate is given in terms of molar concentrations. These are the concentration, no, these are the molar concentration of the reactant with each term raised to some power. This is the power, which may or may not be same as the stoichiometric coefficient of the reacting species in balanced chemical reaction. Remember, the chemical reaction should be balanced. Now let us take an example here. Example: when nitrous oxide reacts with O2, it produced nitric oxide, NO, NO2. Here the rate is given by K, concentration of NO square into concentration of O2. That means here rate should be 1 plus 2. 2 plus 1 is 3. Okay. Next, see. Next is the order of a reaction. Order of a reaction. Now, order of a reaction is the sum of the power of the concentration present in the experimentally defined rate law equations. Okay. Remember this one. Rate law equation is expressed experimentally, not theoretically. Okay. Now, first one, let us take an example. When 2 moles of ammonia react, okay, or dissociated to form 1 mole of nitrogen gas and 3 moles of hydrogen gas, and the reaction rate is given by K, concentration of NH3 to the power 0. Concentration of NH3 to the power 0, that means R equal to K. That means anything if it has power of 0, it will become 1. That means it becomes 1, R equal to K. Then it is 0 order reaction, since here is 0 order reaction. Next, Now see why it is 0. It said no, sum the power of the concentrations. Here is the concentrations, sum of the power. One concentration is there, the power of the concentration is 0. That's why here is 0 order. Next thing is the when 2 moles of nitrogen pentoxide dissociated to form 4 moles of nitrogen dioxide plus oxygen molecule. Okay, and the experimentally reaction rate is given by K into concentration of N2O5 to the power 1. Since here is 1, the reaction order is first order reaction. That order is 1. You can say first order reaction. Third example. When 2 moles of NO2 gas reacts with 1 mole of fluorine gas, it produces 2 mole of NO2F. Okay, and the reaction rate is given by K concentration of NO2 to the power 1 into concentration of F2 to the power 1. Since here is 1, here is 1, if we sum this to power, we will get 2. That means the order of the reaction is 2. That is second order reaction. Last case. Suppose here when what is this? Ethanoate. When ethanoate, that means ethanoate when dissociated, it forms methane and carbon monoxide. Okay, carbon monoxide. The reaction rate is given by K equal to concentration of methanoate to the power 3/2. This 3/2, remember, this is an fraction and is experimentally determined. That's why the order of this reaction is 3/2. Fractional order 3/2. Okay. Now from this concept, what can you say? The order of a reaction is simply the power. That means sum of the power of the concentrations. It is expressed by experimentally, not theoretically. Second thing, the order of reactions may be in fraction. Okay. Next thing is the order of a reaction can be 0 also. Order of a reaction can be 0 also. Now next topic is the very important topic. Our is the molecularity of a reaction. Molecularity. What is molecularity? Molecularity means the number of atom, ions or molecule in the reactants involved in the reaction. Number of atom, ion or molecule involved in the reaction is the molecularity. Suppose here is a schematic reactions. A plus B goes to C plus D. The number of reactant is the A number of A, that means small a number of capital A and small b number of capital B. The molecularity should be A plus B, small a plus small b. Okay, that means molecularity is the number of atom, ion or molecule in the reactant. This one is the molecularity. See, what is the difference between molecularity and the order of a reaction? First difference is the sum of order is the sum of the exponent of the concentrations of reactant in rate law. That means the sum of the power of the concentration of the reactant in rate law is the order, and molecularity is the total number of ion, atoms or molecule in the reactants involved in the reactions. Okay. Next difference is the order may be 0 or fractions, but the molecularity should be whole number except 0. Okay. Order is experimentally determined, but molecularity is theoretically determined. Order of a complex reaction can be determined, but the molecularity of a complex reaction cannot be determined. Now, complex reaction means lots of reactant molecules are reacting simultaneously. Okay, in a very complex way. These are complex reactions. And order of a complex reaction can be determined by a specific or very sophisticated experiments. But molecularity of a complex reaction cannot be determined either theoretically or experimentally. Okay, thank you.